So welcome everyone to this last talk in the series on quantum PDEs. And it's a pleasure to have today Jacob Shapiro talking to us about tight binding limits in strong magnetic fields and the integer quantum Hall effect. Thank you, Jacob.
Thank you very much for the invitation. I'm happy to be here. I will talk about a recent project that is based on joint work with Fefferman and Weinstein, and it sort of connects two what would have been separate questions: one about tight binding, and the other one about topology in physics. I guess the latter is a little bit more recent, a little bit less known to wider communities. So perhaps I'll start with just motivating that field for those of you who are not so familiar with it, especially in the PDE community. It's perhaps a bit less known. So topology in physics is a phrase that is used in order to talk about the application of in particular algebraic topology in physics, and the kind of physics that we want to do. Of course, algebraic topology is useful in many areas of physics. In the standard model, it comes up in gauge theories, but here rather we want to concentrate on the condensed matter or solid state physics. So really the context that we want to concentrate on is electrons that move in solids. Moreover, I'm going to assume that they are non-interacting outside of employing the Pauli exclusion principle. In that sense, they will interact, but otherwise I ignore interactions. And moreover, let me just for a few minutes work in the tight binding approximation. So that means that my real space is a discrete countable set. That's just for a few minutes, as I said. And so in order to describe a system, I need to pick a Hamiltonian. A Hamiltonian H, which is some bounded linear operator on, let's say, L2 of ZD, and you might want to include some internal degrees of freedom, so you tensor with Cn, that might be spin or sublattice symmetry or whatever. Everything would be encoded in this Cn. And we ask that this operator is, of course, self-adjoint, so that the energy is real. That's a basic requirement. A little bit more constraining requirement is to ask for locality. So what we want is that the matrix elements in the position basis, which I denote by HXY, so XY would be 2 points in ZD, and so HXY would be an n by n matrix, really. And so I take its norm and I ask that it would decay as X and Y go farther away from each other. So one possible estimate that you might want to ask for is this one. And really you have to ask for it. If you don't, then your system is in a sense non-physical. And when you do, then the story of algebraic topology becomes non-trivial. So really that is something that you should do. Okay, that's fine. But it turns out that in order to still get interesting objects, we have to make one further constraint, and that constraint would be to ask that the solid that we talk about corresponds to an insulator. There is no a priori reason why you talk only about insulators, and indeed some people started talking recently about semi-metals and other exotic materials, but the most classical setting is to ask for an insulator. That's the setting in which the integer quantum Hall takes place. And so one mathematical way to phrase what an insulator is to ask that there is a spectral gap. That turns out to yield an insulator. There are more general conditions, but this would do for now. And well, I'm talking about bounded linear operators on a discrete space. So I might have used the discrete Laplacian and then maybe some bounded potential. So of course, the spectrum itself is probably going to be bounded already. So the requirement that the spectrum has a gap is not really that it's not the whole real line. That would still be uninteresting. Really what you want to ask for is that it has at least two connected components. So the picture that you imagine is that there might be at least two bands, and then you want to ask that there is some value of Fermi energy where you could put where you would find spectrum below, spectrum above, but right in the middle there is no spectrum, and that is what would make the story interesting. Okay, and so if you make all of these requirements, then it turns out that interesting things in algebraic topology can arise. So let me not talk about the most general theory, but just give you a toy example of how that would come about. So indeed, that toy example would correspond to the integer quantum Hall effect, which is known to be in 2 dimensions. So let's take 2 dimensions, and let's furthermore take a number of degrees of freedom per lattice I to be 2. So you have sort of a 2-level system. And I'm going to make a perhaps unphysical, but mathematically very convenient assumption of translation invariance, which means that these matrix elements can be written as follows. And when you have this translation invariance, then instead of talking about some operator H, which is bounded linear operator on L2 of Z2 tensor C2, instead that turns out to be equal to maps. Let's call them H tilde from the 2 taux once you do the Bloch decomposition or Fourier series into 2x2 matrices, which are furthermore Hermitian. And because of the gap condition, the 2 eigenvalues never touch. So I guess you could write it as saying this. Moreover, there's another important point about this, and that would be the requirement of locality. Locality turns into a certain regularity in momentum space, namely this type of off-diagonal decay that you have in real space would correspond to regularity of this map as a function of the 2 taux. And so, for example, it would be smooth. So that's once you say the word smooth, that's sort of when you can start thinking about algebraic topology. And now you can probably already imagine what's going to happen. I want to consider the space of all such physical systems that obey this requirement in this restricted version of the story where I use translation invariance and where I have only 2 degrees of freedom per lattice site. But still, I want to study the shape or you know, whether there are holes in this space of physical systems. And by massaging the problem a little bit, I realized that really what I want to consider is the family of all smooth maps from the 2 taux into these 2x2 Hermitian matrices where the 2 eigenvalues are never degenerate. Okay, so if you think for a minute, then you realize that this space of 2x2 Hermitian matrices with non-degenerate eigenvalues really can be encoded by asking for a one-dimensional subspace within C2. Why? Because you can just ask for the projection onto the lowest eigenvalue. And because the eigenvalues never touch, then that projection is always well-defined. So that topological space is called the Grassmannian of one-dimensional subspaces within C2. And that, furthermore, is known to be isomorphic to the two-sphere, or sometimes also called the Bloch sphere in the context of quantum mechanics or quantum information. So we realized that what we want to understand is somehow the shape or the what would technically be called the space of the set of path-connected components of smooth maps from the two toes into the two-sphere. And suddenly this looks very much like a problem in algebraic topology, even though it started from quantum mechanics.
Jacob?
Yes.
Sorry, Jacob, can I interrupt you for a second?
Please, with pleasure.
Yeah. How your spectral picture with the Fermi energy related to what you're saying now?
Essentially, by asking that there is a spectral gap, I encode it by saying that the two eigenvalues never touch, and that's how I use the condition.
Okay, so there, you have two bands and the gap between two bands. So you
Exactly.
don't have a. So you're talking. Okay, so you assume that on background you have periodic potential, right?
Yeah.
And then this stores is the Brillouin zone of this periodic
Exactly.
potential.
Yes, exactly.
Okay, that's the other question is, since you're talking about topology, why do I care about smooth maps? Not just continuous maps or whatever.
Oh, okay. Thank you for the question. So that was going to be my next point, which is that it turns out, I mean, indeed, in algebraic topology, it's not so convenient to talk about smooth maps, but it turns out that there's an approximation theorem or an embedding theorem that says that we can just as well talk about the family of continuous maps from the two toes to the two sphere. So that would land us in a much more classical place. Okay, and then a space of all continuous maps from two toes to two spheres is something that we understand rather well. It's I guess classical by now. You can think of the two toes as or maps from the two toes into a space. There would essentially be three things that you have to understand. There would be one loop, one type of loop, and then there would be another type of loop. And then you would have to sort of understand the two-dimensional remainder of the map. However, the two-sphere is simply connected, which means that any loop on the two-sphere can be contracted to a point. So these two red and blue loops actually don't contribute anything to the classification problem. And so it turns out, I mean, this is a non-trivial statement, but nevertheless, it is true that this is equivalent to classifying the space of maps from two-sphere to two-sphere, which is by definition pi2, the fundamental group of the two-sphere, which again is a non-trivial statement, but is widely known that this is isomorphic to the integers, to z. All right. So we sort of, in this restricted context, we fully understand the problem, and we realize that this set of physical systems are somehow classified by the integers. We could have actually done it in greater generality because remember that we took n equal to 2, we can generalize it to any number, actually. And also, then you might have a situation where you have 4 bands and you pick your Fermi energy always above the first 2. And you can easily see that would correspond to talking about the space of, let's say, if these are K bands, then you want the space of the Grassmannian of K-dimensional subspaces within Cn. okay, and the space of maps from the two toes to this Riemannian is actually turns out to be the set of isomorphism classes of vector bundles when you take the necessary limits of vector bundles above the two toes. And so you can start really making a systematic study to talk about Chern classes and Chern numbers, but let me not go into that because that's not really what I want to focus on. I just want to say that if you assume this translation invariance, then many classical things apply and that story becomes quite convenient. But what is this Z? What is this integer? It turns out that, that it's not just some mysterious number, but it's something that you can actually measure in the laboratory about your system. So how that would go, that brings us to talk about the integer quantum Hall effect. And the toy example that I gave is an example of the integer quantum Hall effect. So we work in 2 dimensions. Again, we have electrons, which are moving in a strong perpendicular magnetic field. All right, so you imagine you have some 2-dimensional material and you have a magnetic field that penetrates the material, and you have the electrons that are moving. And so just the presence of the magnetic field, at least classically, means that you'll have these cyclotron orbits that just go around in circles. And the fact they go around in circles, in particular that they have closed trajectories, means that they are localized. They are not really moving, and as such, the system is an insulator. That's a very intuitive statement. But in the integer quantum Hall effect, what you want to do is actually apply a voltage in the 2 direction. And once you do, then again, classically speaking, you would see that these orbits start to drift. And they drift in the 1 direction. Even though the voltage is in the 2 direction, the current is in the 1 direction. And so Hall, that was already more than 100 years ago, I think. Hall is the first person who described this effect, and so there is the Hall effect. And he realized this interesting phenomenon that there is this transversal current, and he wanted to talk about the conductivity associated with this current. So you take the ratio of the of I1 with V2, and that's the definition of this Hall conductivity. Now it is a fact that this Hall conductivity turns out in appropriate units to be in 1/2 pi of the integers, which is an astonishing thing because it's a macroscopic system, right? It's not a hydrogen atom whose energy levels are quantized. This is something that you can really measure with an ohmmeter or whatever, and you would see a certain quantization, which is macroscopic. So it's sort of a macroscopic quantum mechanical effect. And well, okay, I hope by now it's sort of clear where the story would converge to, in the sense that this physical observable and this sort of label in an algebraic topology classification scheme are actually one and the same thing. So this is a highly non-trivial statement, but it is indeed true. I guess the first credit of the first people who deserve credit for this statement would be maybe TK and N, Cowles and collaborators. But then there were, I guess, a bit more mathematical explanations that you know, really used algebraic topology, Avron, Zeiler, and Simon. And then Belisard and collaborators had some very meaningful analysis of this story. And so what is the explanation? The explanation is that to calculate this Hall conductivity, I mean, okay, I defined what it is in terms of classical quantities, macroscopic quantities, but But really, if you want to calculate what it is, then you start doing linear response theory. So you really should use the Kubo formalism or Kubo formula in order to write down an initial formula for what this is, and then you work quite hard, and some parts of this story are not even fully rigorous yet. But if you use the Kubo formula, then it turns out that you can connect it to this Chern number, to this Z label of the physical system that you work with, and really you even have a formula. So the whole conductivity of a Hamiltonian equals 1 over 2 pi, an integral over the 2 tau's of, I'm now again in the translation invariant setting. So it would equal the integral over this particular form. And so, well, it's not clear from this particular formula, but it is indeed an integer. 1 over, or let's say 2 pi of this quantity is an integer, and it is known as the Chern number. So, you know, what is so important about this is not necessarily that we were able to make some algebraic topological classification of the system, but moreover, that we were able to connect it to a physical and even macroscopic quantity that we could measure in the laboratory. And that's really the point of this story here. And that's why it's so interesting and garnered so much attention of the scientific community in the past 4 decades since it was discovered. Okay.
Quick interruption. So P wiggle is the projection, eigenprojection on this band.
Right. It's a 2 by 2. It's a 2 by 2 matrix.
On the fiber, yeah.
And it would project onto lowest eigenvalue subspace. Thank you. More generally, you know, you should say that the whole conductivity depends on where you put the Fermi energy. So really, you know, that there should be a Fermi energy that also is a parameter of this calculation. And then, you know, this would be the particular measurable function applied on the Hamiltonian. This is called Fermi projection. So, right, so the formula only makes sense if the Fermi energy is not in the spectrum. Of course, you can generalize this statement and consider what is called a disordered mobility gap regime. Let me not get into that. Okay. So let us, however, speak about more general formulation of this Chern number of this whole conductivity that will actually be the starting point of what I want to say, because we want to consider actually disordered systems and do tight binding approximations on disordered systems. So more generally, it turns out that you could write the whole conductivity associated with some projection, so with a Hamiltonian and the Fermi energy, as an index, a Fredholm index of an operator PUP plus P perp. And okay, P, you already know what it is. It's given by this formula. So I had to choose a Fermi energy, and I had to make sure that it doesn't sit inside the spectrum. Fine. What is U? U is a unitary multiplication operator that is should be thought of as a flux insertion at the origin. So x1 and x2 are position operators in the 1 and 2 direction. And so, okay, now I should tell you, in case you're not very familiar, what is this index? So take some operator f a bounded linear operator on your Hilbert space, general Hilbert space, separable should be. And you should ask that its kernel and that its co-kernel are both finite. And if both of these conditions are true, then it turns out that this is what is known as Fredholm operator, and then the index of such an operator is a well-defined object, which we have as the dimension of the kernel minus the dimension of the kernel of the adjoint. So the kernel of the adjoint is equal or isomorphic to the co-kernel. And for us, it's more convenient to talk about kernel of the adjoint. And phrased in this way, it's very clear that this is a priori an integer. So unlike the previous formula that we had, this one, where one had to work a little bit to understand why this is an integer, here you don't have to work at all. It's just from definition an integer. And what is, however, a bit less clear is why these conditions are true. And that is related to the gap condition on the Hamiltonian, which implies certain decay of the integral kernel of P. And ultimately, that is why you would have these constraints. So I don't want to say too much about Fredholm operators, but I have to mention two basic facts, and these facts were crucial in our proof of connecting topological invariants of tight binding systems with the continuum counterparts, and namely index turns out to be stable under compact and the norm continuous perturbations. So you could take this operator F, you could add any compact perturbation to it, it remains Fredholm and the index is the same, or you could add a little bit perturbation that is norm continuous, and again, it remains Fredholm and the index is the same. And it turns out that we need both of these stability types in order to go through with the proof, or at least we use both of them, which is a bit surprising to me, but really both needed to be used. All right. So it turns out that this formula holds in great generality. As I already alluded to, you can replace the spectral condition with a more general disordered mobility gap condition. That I don't want to do right now, but what you can also say is that this formula holds in the continuum as well. So by the way, I think the first person who wrote this formula were Belisard and collaborators, Van Elst and Schulz-Baldes, in '94. I believe that was the first attribution, but one has to check. So this formula holds in the continuum too, and indeed there is no particular reason why the discussion should take place in the discrete setting. The integer quantum Hall effect is something that you can just as well talk about when talking about Schrodinger operators on L2 of R2. You know, and your Hamiltonian would be a pseudo-differential operator, and why not? Indeed, in fact, why do the opposite? Which brings me to the next point, and that's really the beginning of what we did. So far, I really just gave you context to the story, to what we think about topology in physics, but now starts the actual work that we did.
Okay. Sorry, Jacob, to interrupt you again. So by formula, you mean equality of these two expressions for the Chern number, expression in terms of the projections, in terms of the commutator of projections and before, and this one, and in terms of the index of Fredholm operators.
That's right. So I actually did not write down, but thank you for mentioning the expression of the Kubo formula in terms of the double commutator. there is such an expression, the trace of a double commutator involving the projections. That trace formula comes from the Kubo formula. It's not a priori clear why that formula yields an integer. And there is work that one can do, that's what Belisar did, in order to essentially use what is known as Fedosov formula to rewrite this trace as the index of a particular operator. Once you do, then many topological properties pop up, like the integrality, like the stability. So that's the value of using this index formulation.
Right. And by commutator, you mean the formula which you had before, above?
Yes, that would be this formula, which you can just as well write also without using translation.
Okay.
Right. Is it okay? Shall I go on? I assume so. Okay. So, right. So this brings me to the discussion of continuum versus discrete. So, a priori, there is no when you grow up and you study physics as a physics student, and especially if you think about quantum field theory or high energy physics, you really think in a very fundamental way that space is a continuum set. It should be RD, and there has to be a particular reason why you would use any other choice. And so, here I've used Z2, and one can always say, or have sort of a very liberal approach to physics and say, I'll use the model that gives me a non-trivial description of the effect that I want to talk about. And in this sense, it's justified to use Z2. But otherwise, it turns out that all of these, or let's say most of these studies on the integer quantum Hall effect and topological insulators, this really became an industry in physics now. It's very, very big. But a lot of these studies are really made in the discrete setting on Z2 or ZD more generally. And one would like to ask, why is it justified? Why is it valid to use this discrete description of the system? And this question is not new at all. I mean, the tight binding approximation is a tool that has been used in physics in the early 20th century since that time. So, of course, when you talk about electrons in solids, the energies that they will attain will be very, very small. They will not be relativistic. So if you think about a continuum operator that has a certain spectrum, let's say it's bounded from below, it has some bands, but these bands do not end. It has an unbounded spectrum, but the electron has bounded energies. It will not suddenly shoot off with relativistic velocities in a solid. So in that sense, it's perfectly judicious to just cut the operator and talk about the bounded region of the spectrum and also the dynamical equivalent of that. And that is what is very usually done. This is called the tight binding approximation. So what's the problem? The problem is that what we are talking about are topological properties. We want to talk about classification of the system. And so a basic sort of a structural question arises, which is, do we lose or distort any topological information when we use the tight binding approximation? One would hope that the answer is we do not lose anything, but it's not clear. I mean, it deserves a proof. Okay, and that is the proof that we came up with. So it's a theorem that in the integer quantum Hall effect, under many conditions that I will stipulate in a minute, I need to set up a certain language for that. But
could I jump in with a question?
Yes, please.
So lots of topological notions can be captured with discrete structures, simplicial complexes. In that sense, that's a discrete object encoding a topological invariant. Is that a way to think about this paradox here of the discretized ZD and the extent to which it can potentially capture topological notions which you might think are lost if you go there?
I mean, in a metaphorical sense, I would say yes, but more concretely, not really, because what we discretize is indeed space, but what we care about, the classification is not that of space, of real space, but really it's a classification of quantum mechanical operators on space. So really, you want to ask that, when you have discretized space, you got a new quantum mechanical operator, indeed a new family of such operators, and whether the classification scheme of this family of operators remained the same, whether the description was accurate in that prism.
Yeah. And if I could just sort of a language issue perhaps, but sometimes physicists will say that going from the continuous R to the lattice is an ultraviolet cutoff. It's
Exactly.
a regularization. So is that in some sense what you're also talking about when you're looking at this energy spectrum?
Exactly. That's exactly the point.
Okay, good. Thank you.
So, right. So we have an ultraviolet problem when we talk about continuum operators, and you would hope that these ultraviolet divergences have nothing to do with the problem at hand, but this deserves a proof. It's not a priori clear.
No, I agreed with that.
All right. So the theorem is that in the integer quantum Hall effect, under certain fine print conditions that I will get to in a minute, but let me not say what they are right now, we don't lose any information, or rather, we do not lose or distort topological invariance. Namely, the invariants of the continuum agree with the invariants of the tight binding systems, which are the limits of these continuum systems. And so really what I'll do in the rest of the talk is explain what are these conditions and how to phrase them. But the theorem, the main theorem is, yes, indeed, you do have agreement and you don't distort anything. And, okay, so this was quite involved to prove, but you would say, it's always true. It was expected. It's not surprising. No, not really. So actually, there are counterexamples of other symmetry classes, other kind of topological insulators where this statement is not so easy to make, and indeed, it's not even clear what are the continuum analogs of discrete systems. For example, one-dimensional chiral systems. It's not so clear that you can prove a similar theorem for such systems. So really the theorem does have counterexamples. All right. So now I'll spend the rest of the time just talking about what these conditions are and hopefully getting to what is the scheme of the proof and the scheme of just how to do tight binding. So actually there are two theorems here, because before you may talk about the topological invariance at all, you have to set up a tight binding scheme. And apparently that has not been done in the context of a non-trivial integer quantum Hall effect. So of course, tight binding schemes have been rigorously proven. That's a classical topic in mathematical physics. The names, the main names that should be mentioned are Helfer and Sjoster, and then there's an important paper by Carlson. But in the limit of very strong magnetic field, and as I said, that's what we need for non-trivial integer quantum Hall effect, I'm not aware that that was done. So the first thing you really have to set up is what is a tight binding approximation at all. And so let me try to motivate that. So there are many continuum models of the integer quantum Hall effect, but I want to concentrate on one particular picture that is especially suggestive towards a tight binding limit. So in a tight binding limit, you have a discrete space. So we really want some kind of structure that would force the discreteness. And one thing that you can imagine is to put a set of wells along a regular lattice, or any kind of lattice for that matter. And these wells are going to generate bound states that would be localized in the centers. And then the electron could either be bound to one of these wells, or it could tunnel from one well to the next, or rather hop. And then we can imagine that in the limit that the depth of the wells goes to infinity or minus infinity, you more and more see a discrete picture. So there is, I just mentioned that there is an alternative way to derive a tight binding approximation that is using Vernier functions. So Vernier functions are, in a sense, the inverse Fourier transform of Bloch functions. And so in order to talk about them, you really want to have translation invariance. At least naturally, it's really naturally suggests that. And actually, we don't want to use translation invariance for various reasons. The first reason is that we want to be able to include disorder. So this lattice of wells need not be Z2. For example, it could be Z times N. And when it's Z times N, it would model a system that has a boundary that's called an edge system. And we want to understand both systems on the same footing. However, here in the second one, you cannot do Bloch decomposition on one of the axes. Or you can even consider a much more general a Delaunay set where you know the centers of the wells are somehow could be any random process, and only want is just that there's a minimal pairwise distance so that they don't suddenly collapse onto one another. But there is maybe even a philosophical objection to use translation invariance, in the sense that it might lead or might have led to a simpler proof, but you somehow don't want to mix one pleasure with another pleasure. You want to know that this fact is true, not because of translation invariance. It's true in general. It's not because of having Bloch decomposition. All right.
Sorry, Jacob, but translation invariance, I mean invariance under lattice translations.
That's right. That's right. In that context, I could have done Bloch decomposition, even though I have a magnetic vector potential, or I will have in a minute. But you can use sort of enlarged magnetic unit cells and then still do Bloch decomposition. Or could have done, but I exactly don't want to do it.
Can I ask another question in that regard? So you often hear in the topological insulator world, symmetry protected topological state. So to give up on translation symmetry, that I guess none of the topological states you have in mind are protected by that. That's
right. When people talk about symmetry protection, they actually, I mean, there is a discussion about space symmetries, but usually the more classical thing is, for example, time reversal invariance.
Yeah. Mm-hmm.
So indeed, the integer quantum Hall effect has a magnetic field which breaks time reversal invariance. So we really exactly want to break it. It turns out that time reversal invariant systems also have some interesting features, topological features, but I am not going to talk about it. So
okay, thanks.
Sure. Okay, so the kind of Hamiltonian that I want to write down is going to be a magnetic kinetic energy, and then a sum over some lattice, let's call it G, of some one atom well function. So A is the magnetic vector potential, which we want to model a constant perpendicular magnetic field, so we can just take it to be the cross product of the third unit vector with the x position operator. B is going to be the magnetic field strength. Lambda is the asymptotic parameter, which is the well depth. And V is going to be the shape of each of these wells that I do here. So it's a map from R2 into, let's say, -1 until 0. So this just means that it's going to be bounded. Because I anyway control the depth with another parameter. And I ask for certain conditions. Now, these conditions, most of them are probably not essential, but they just make the discussion a little bit more pleasant, let's say. So the first one is that it's compactly supported. The second one is that it's smooth. That will help. And the third one, I will stipulate this condition in a minute. But there is a third condition. It relates to the single atom Hamiltonian. All right. And then G is my lattice, is the set of centers of these atoms. And really, it should be an infinite set, a countably infinite set. And I make another requirement on it. I ask that pairwise minimal distance is A, and it's greater than 0 as lambda goes to infinity. So, you could still imagine even weird situations where this lattice even depends on your asymptotic parameter. We allow that, that's fine. We only ask that if that happens, the pairwise distances don't suddenly collapse to 0. So should be, let's say, order 1 as lambda goes to infinity. And then you want a certain relationship, or it doesn't have to be, but it makes life very easy if you have a condition that says that the radius of the well is smaller than twice this minimal distance, so that you never have overlaps. This is ruled out. That just makes life very much easier. And so an example for such a set would exactly be Z2 or Z times N, or even any kind of random set, whatever you want. All right. And now it's clear that tight binding limit corresponds to lambda going to infinity. However, what happens with B? Yes.
Sorry, maybe you said it, but I missed it. Are you thinking that you're thinking that your underlying space is two-dimensional?
I am, yes. Sorry, I should have said that this is on L2 of R2. That's very important, thank you.
And E3 is the one that goes outside of the plane, the vector?
Yes, right, it's the one that goes out of the plane.
Thank you.
So what to do with B? Does it scale with lambda? Does it not? So it turns out that there's a result by Nakamura and Belisard that say that as lambda goes to infinity, B is fixed. The low energy bands of your Hamiltonian have trivial Chern number. But in exploring the tight binding limit, we exactly want the low energy spectrum. So that's bad news for us. So that means that if you have any hope of studying a non-trivial effect, you better send B to infinity too. It turns out that it is natural to take B proportional to exactly lambda, because when you do that, then you can make very nice statements about your system. In the case that V has a unique minimum, something that I've not asked for, but it's very natural to ask for, because when you do, then you can pretend that your well kind of looks like a simple harmonic oscillator at its bottom, which is a system that you can solve. And it's certainly very nice if you have this scaling so that you can actually say that it converges to some scale-free system. So we will use this scaling indeed. And so let me just briefly speak about the single atom. So it has a kinetic energy and it has just one potential. So let me call phi the ground state. It's the state of lowest energy, and with energy E. So now I can tell you what are these dots that I asked for here. So the condition is, first of all, E should be proportional to minus lambda squared, and then you will be some order lambda. And next excited state we ask that the difference between them is going to be of order 1. So we don't want that suddenly, as lambda goes to infinity, the gap, the single atom gap, collapses to 0. So that would be one requirement, or that's not really a requirement, that's true. We know that this is true in many different cases. This is an actual requirement. And second requirement that I will ask for, and that's because of some technical reasons that come up later, is that V is radial, which is kind of natural. I mean, that does not rule out the system being disordered, because the disorder can be in the positions of the wells, but then each well itself is radial. But moreover, we ask that it's radial such that the ground state itself is also radial. And that's really a decisive assumption. And probably if you don't make this assumption of being radial, there are some weird problems that can come up. And all right, because of compact support, you actually know by something which is very similar to an Agmon estimate that outside of the well, you have the following estimate. You have Gaussian decay. So the usual Agmon estimate is exponential decay, but here, because of the magnetic field, you upgrade to Gaussian decay outside of the well. All right. So I see that my time is almost up. So I guess I should summarize. But at least now you know what the assumptions are. In these assumptions, so I guess the conclusion would be that under the assumptions of stipulated above, on your lattice G and your one atom potential V, there exists some tight binding operator on the discrete space such that you have some quantity rho, which is some exponentially decaying number, and it's an emergent asymptotic parameter, such that if you scale your Hamiltonian by this number, and you also subtract the energy, then it converges as lambda goes to infinity to your tight binding Hamiltonian in norm-resolvent sense. So that means I have to pick a spectral parameter z in the complex plane outside of the spectrum of the tight binding Hamiltonian, so that the resolvent of this operator converges in norm to the resolvent of the tight binding operator. Actually, we even have some quantitative bounds as lambda goes to infinity. This norm-resolvent convergence immediately implies, using the Riesz formula, that the spectral projections are close by in norm. And as you can imagine already, that sort of already leads your thinking into how you would prove that the topological invariants are the same. Of course, here you know that only makes sense if this tight binding limit indeed has a gap. And so, our statement is that in some situations it will, in some situations it won't. That really depends on the lattice that you take. For example, if you take Z2, then you get exactly the Harper model. The Harper model is a classical model of integer quantum Hall effect, and it is known to have gaps, and some of these gaps have non-trivial Hall effect or Chern number. And so if you use this, then you would get a non-trivial result, first about the dynamics, the long-term dynamics of the system, then about the spectral projections, or even more generally about the functional calculus. And from there, you still have to work, but from there, your path is sort of paved towards proving that topological invariants agree. So in principle, that approach really concentrated on the integer quantum Hall effect, and it's really using the lowest, the ground state, in order to build statements about the lowest band. So really, we are only talking about the lowest band, and maybe it has some sub-bands of the Hamiltonian, but more generally, you could consider other symmetry classes. You could consider time reversal invariant systems, or in principle, there's a whole periodic table of these models, and each of them actually has an index formula. So kind of the strategy should at least inspire also these other models. So I guess my time is up. So thank you very much.
Thank you very much, Jacob. Beautiful talk. Thank you. Let's see if we have questions.
I have a couple of questions. So first of all, about the you said that topological invariants agree. So what you mean by that? I guess what you mean by that is that you have a class of Hamiltonians which includes tight binding and continuous ones, and the time binding approximation is in the same equivalence class, topological sector, topological equivalence class as the continuous one.
Actually, the statement is a little bit more concrete, perhaps weaker than that. The statement would be that the index computed on L2 of R2 of this PUP plus P perp equals the index computed on L2 of your lattice G of P tight binding, U tight binding So really, it is a numerical statement between two numbers. And of course, you know, p-tight binding is really just the spectral projection, assuming that there is a gap for the tight binding Hamiltonian, and this is related to the above one because it has to choose the same gap. It has to look like this.
Okay. So, and the second question is that goes into the core of your kind of a technical assumption. What happens if you take positive temperatures?
That's a good question, and it's outside of the universe of this story.
I understand. So you don't have a gap in this case, but it's you have kind of for small temperatures, you have exponentially small tails there in the gap. So you think that one might be able to still some kind of work out this.
It is possible. I have to confess that I have not really heard about physicists who talk about positive temperatures, but of course it has to be because real systems don't work at absolute zero.
Of course, and kind of naturally you want to replace your Fermi projection by Fermi-Dirac distribution,
right?
So which is written here in exactly on this page at the bottom of the page,
right?
You want to replace chi characteristic function by Fermi-Dirac distribution. So if P is not a projection anymore, it's approximate projection.
Right. You know, I have to say that at least partly there is some hope that this could be achieved just because the Fredholm index is so kind when you work with it. It allows you to make these deformations, and so actually just as well you could replace a projection with a smooth function. Indeed, by the way, that was something we had to do somewhere in the technical details of the edge proof. So maybe there is hope.
Okay, thank you.
I think there's a raised hand by Stephen Watson. Do you have a question?
Yeah, thanks. Really lovely talk. Sorry, I missed the beginning of it, actually. I just caught the second half. So my question may have been, at the end there, you mentioned this emergent constant. Could you say something about that?
Oh, yes. Thanks for the question. So the tight binding Hamiltonian turns out to be related to these matrix elements, phi n. I remind you that E is the ground state energy of the single atom. So really E would be sitting somewhere in the middle of this band, and phi m. And what I mean by phi n, phi m subscript is that I take my ground state and I translate it to the centers of the wells somewhere. And that translation, by the way, is not ordinary translation, but it's magnetic translation, which is what would commute with the magnetic kinetic energy. Anyways, this set of the translate of the atomic orbitals is what builds actually a basis for this smallest band here. And rho turns out to be the largest of these matrix elements. So, you know, you have phi, let's say at the origin, let's say one of these centers of the wells is at the origin, and the other one, let's say at A, which is the minimal lattice spacing, let's say in the horizontal direction, doesn't matter, because rotations just change a phase. And take the largest of these matrix elements, and that actually also decays exponentially, so it's kind of difficult, but the largest one of them turns out to be the correct quantity by which you want to scale all matrix elements, and if you do that, then you get H tight binding, which now doesn't depend on lambda. It's scale free. And so really the main technical difficulty why magnetic fields are so hard here is because in dealing with this rho, with this emergent asymptotic parameter, there is a magnetic translation. So that includes a phase. This phase depends on lambda. So as lambda goes to infinity, it oscillates harder and harder. And so you have to estimate from below an integral that oscillates faster and faster. And that is related to another point that I didn't get to talk to, but it's connected to the magnetic double well eigenvalue splitting to estimate this quantity from below.
Okay. So C is instant-on action.
Exactly. Thank you.
Oh, super. Thank you.
C is the instant-on action in the non-magnetic case, and I would be really glad to know what it is in the magnetic case.
Okay, you have to do tunneling in magnetic case.
Right, which, you know, I don't know how to do. So we had to kind of by hand do it, and we are still not sure how to do tunneling in magnetic case because it turns out that then the action, at least if you do things stupidly, which is what I try to do, the action is imaginary. So
you mean complex?
Yes, I mean it has real part, it has imaginary parts.
Right.
So, it's not clear to me how to you know, do this instant-on story when you have a magnetic field. I would be really glad to find out, actually.
But if you do it formally, you in terms of the path integral, you should be able to do it. There's a path integral for the magnetic field.
There is one. I've not seen it, not even in the physics literature.
Yeah, you should look at there's a book by Kleinert and a book by Schulman on the path integrals. They must be there. So,
okay, so as far as I was able to survey the literature, the magnetic double well eigenvalue splitting problem is not a lot of attention.
No, you don't look at the rigorous literature. You look at the physics literature.
Okay.
I'm talking about physics books.
Even there, indeed, there were some papers, but not very many. And I saw one paper from 2014 by Bruning, Dobrokotov, and another person whose name I forget. That it seemed peculiar to me that only in 2014 there was a paper about this.
But check these books. This is by physicists, and they should have it.
Okay.
Kleinert, quite a big encyclopedic book.
Right. Thank you.
And maybe if I could, with a sort of unrelated follow-up, what's known about the dynamics in these problems?
Could you be more specific?
Well, yeah, I mean, so when I think of these topological states, I think of systems, for example, which are quenched or attempted to be quenched into these states from an initial state. So I'm sort of interested to understand, essentially topological ordering dynamics is maybe the idea at the back of my mind. It's a vague notion.
I mean, these are big concepts. I think the integer quantum Hall effect is more simplistic than that.
Oh no, I was just simply to prod or probe your understanding or awareness of that aspect.
I mean, as far as I know, you know, the classical pictures of how we imagine the electrons moving in these drifting orbits or skipping orbits if you are at the boundary and you have applied an electric potential, or they are just closed orbits, closed trajectories, and the system is an insulator if you didn't apply an electric potential. You know, I'm not sure what.
So again, maybe the spirit of the question, if I could just, I mean, if you take critical phenomena in a sort of a classical sense, lots of examinations of what happens when you approach or quench to critical points, also similarly for first order phase transitions. So I guess it's like the dynamic side of me wants to understand sort of parallels of what happens when you, quote, push a system into a desired sort of topological condition, but your initial condition is far from that. So it's the process by which it finds this state.
Right. So that there is such a process here, but you sort of pretend that you're already after the valley, so to speak. So that process relates to the insulator condition. So indeed, in order to get from, let's say, the atomic limit in which all atoms are separated and there is nothing topological, and then you bring them together and something might happen or might not, the gap of the system has to close and reopen again. And exactly when that happens is when you might have a chance to actually get into a topological island, a topologically non-trivial island. But the whole discussion here was within the island.
Yeah, understood. But thanks, Jacob.
Sure.
I think you should.
I was muted.
Stop recording. Stop recording. And
we can thank the speaker again.
Get a bit relaxed. Yeah.
Let's thank Jacob again for the beautiful talk. Thank you so much.
Great.
Thanks everyone for coming and participating to this session. It was great. So hope to see you at their future events.